Everyone, welcome to the video for Module 6.2.1. And this one, we're going to talk about some of the muscle types. We'll start off with skeletal muscles, which we've highlighted extensively in the previous modules. But the skeletal muscles of the muscular system account for almost half of the weight of our bodies. So the human body contains approximately 700 skeletal muscles that differ widely in size, shape, and function. And although individual skeletal muscle fibers contract the same way and to the same degree, the performance of skeletal muscle varies depending on the way the muscle fibers are organized and how the muscles attach to the skeleton. All muscle fibers have to have at least 2 points of attachment. You either have the origin, which is the fixed attachment point, or the insertion, which is the movable attachment point. The origin is typically proximal to the insertion, where the body is in an anatomical position. So when complex movements occur, muscles commonly work in groups rather than individually. Their cooperation improves the efficiency of particular movement. For example, large muscles of the limb produce flexion or extension over an extended range of motion. And within that, you have a few different types of things. You can have the agonist, which is a muscle that provides the major force for producing the specific movement, also known as the prime mover. You can have the antagonist, which is the muscles that oppose or reverse a particular movement. You can have synergists, which are muscles that help prime movers. They generally add just a little extra force to the same movement or undesirable or unnecessary movements that might occur as the prime movers contract. And you have fixators, when synergists immobilize a bone or a muscle's origin. This is just an example of prime movers and synergist here. In the example that you see, the biceps brachii flex over the lower arm, and then the brachioradialis in the forearm and the brachialis that are located deep to the biceps in the upper arm are both synergists that aid in that motion. Getting into some of the muscle shapes and fiber alignments, you can have some of the fascicle organization here. We can have circular, which are also called sphincter muscles, in which the fascicles are arranged in concentric rings. An example of this is the orbicularis oris. You can have convergent, when the muscle has a broad origin and the fascicles converge towards a single tendon or an insertion. For example, the pectoralis major. You have parallel, in which the long axis of the fascicles run parallel to the long axis of the muscle. And these are generally strap-like muscles, for example, the sartorius and the biceps brachii. And you have pinnate, which the fascicles are short and they attach obliquely to a central tendon that runs the length of the muscle. Within that pinnate, you can have the fascicles insert. You can have unipinnate, in which the fascicles insert only into one side of the tendon. For example, the extensus digitorum longus. You can have bipinnate, in which the fascicle insert into the tendon from the opposite side, so that the muscle grain kind of resembles a feather. For example, the rectus femoris. And then you have multipinnate, in which the arrangement looks like many feathers that are situated side by side. For example, the deltoid. So I just want everyone to know that within the book and the unit, they start to talk about some mechanics and levers. We don't have a lot of time to cover that here, and we won't be tested on that info, but just in case you needed to hear it, muscle mechanisms are often like levers that if you've taken a physics course, you know a little bit about that. So the operation of most skeletal muscles involves the use of leverage and lever system. Basically, a lever is a rigid bar, such as a board or crossbow or not a crossbow, a crossbar or a bone that moves on a fixed point, or what we consider called a fulcrum. And when force is applied to it, the applied force or effort is then used in resistance or a load. So in the human body, joints are used as the fulcrums. Your bone acts as lever, and your muscles pivot or provide the effort. Levers can operate in two different ways. They can provide mechanical advantage, in which the load is close to the fulcrum and the effort is applied far from the fulcrum. And this situation requires minimal effort to move a large load and is therefore designed for power. This is considered a power lever. And you can also have mechanical disadvantage, in which the load is far from the fulcrum and the effort is applied near the fulcrum. This situation requires the force to be greater and the load to be moved, but although it cannot move a large load, it can move loads farther and faster. This is called the speed lever. And depending on the relative positions of the three elements, effort, fulcrum, and load, a lever belongs to one of three classes. You have a first class lever, in which the fulcrum lies between the applied force and the load. Example, scissors or other things like that. You have a second class lever in which the load lies between the applied force and the fulcrum, kind of like a wheelbarrow, or a third class lever, in which is the most common levers in the body, in which the applied force is located between the load and the fulcrum. And the example here is tweezers, or in the body, the biceps brachii. All right, we're going to get into the other two types of skeletal muscles here. Sorry, not skeletal muscles, other two types of muscle tissues. Um, so let's talk a little bit about the structure of cardiac muscle tissue. Cardiac muscle cells possess a single centrally located nucleus, and they are uninucleated. Cardiac muscle cells are also relatively small and are columnar shaped, unlike skeletal muscle cells. Cardiac muscle cells also branch. Cardiac muscle cells are also metabolically very active and therefore possess a large number of mitochondria and are rich and supplied with capillaries. Cardiac muscle cells also possess striations because of the highly organized arrangement of the myofibrils into repeated sarcomeres. So, approximately 1% of cardiac muscle cells are capable of generating their own electrical impulse and are therefore called autorhythmic. Cardiac muscle cells possess intercalated disc, where the plasma membranes of two adjacent cardiac muscle cells are extensively intertwined and bound together by gap junctions and desmosomes. These connections help to stabilize the relative position of the adjacent cells. It also allows for a direct electrical, chemical, and mechanical connection between the two muscle cells so that the cardiac muscle cells act as an enormous single cell. This ability to behave as a single coordinated unit is called the functional succinctum. The cardiac muscle cells contract longer than skeletal muscle fiber contraction, primarily due to the differences in membrane permeability. Calcium channels remain open in cardiac muscle cells for an extended period of time, resulting in a prolonged refractory period. Intercalated discs are, again, a specialized contact point between the cardiocytes, and they join cell membranes of adjacent cardiocytes in what we call gap junctions and desmosomes. And these connections help to stabilize the relative positions of the adjacent cell. Also allows, again, a direct electrical, chemical, and mechanical connection between the two muscle cells so that the cardiac muscle cells act as an enormous single unit. And the ability to behave as a single coordinated unit, again, is called the functional succinctum. Some of the functions of cardiac muscle tissue, you have audiorhythmicity, or contraction without neural stimulation, and it's controlled by what we consider pacemaker cells. You also have variable contraction tension, which is controlled by the nervous system. You can have extended contraction time and the prevention of wave summation and technic control by cell membranes. Moving into smooth muscles of the body system, these form around other tissues. Smooth muscles are non-striated, so in blood vessels, they help to regulate blood flow and pressure. In the reproductive and glandular system, they help to produce movements. In the digestive and urinary systems, they help to form sphincters and produce contractions and movements of fluid. In the integumentary system, the erector pili muscle is what causes goosebumps and causes your hairs to stand up on end. Some of the characteristics of smooth muscle cells. Smooth muscle cells are relatively long and slender, and they range from about 5 to 10 micrometers in diameter and 30 to 200 micrometers in length. And although actin and myosin filaments are utilized in the contraction of smooth muscle, they arrange differently from that of what we see in skeletal muscle and cardiac muscle, and there are no sarcomeres or myofibrils. And as a result, there are no striations in smooth muscle, and it's called an unstriated muscle. So remember, the thin fibers, which are actin, are attached to dense bodies rather than Z lines, and the thick filaments, myosin, have more heads per thick filament and are scattered throughout the sarcoplasm. Furthermore, there are no T-tubules, and the sarcoplasmic reticulum forms a loose network throughout the sarcoplasm. Visceral smooth muscle cells have no direct contact with motor neurons, but are connected to each other by gap junctions. So whenever a contraction is stimulated, its electrical signal can spread from cell to cell. We have pace setter cells that are present in areas where peristalsis or rhythmic contraction is necessary. Some of the functional characteristics of smooth muscle cells, you can have excitation or contraction coupling like we saw in skeletal muscles. You can have the length tension relationships, control of the contractions, and then smooth muscle tone, which helps to maintain normal levels of activity, and it's modified by neural, hormonal, and chemical factors. This just rehashes excitation contraction coupling from the previous modules. The length tension relationship that I just mentioned previously is when thick and thin filaments are scattered and the resting length is not related to the tension development. And this functions over a wide range of lengths and plasticity. So the number of pivoting cross bridges depends on the amount of overlap between thick and thin fibers. There's an optimum amount of overlap to produce the greatest amount of tension, but too much or too little overlap reduces the efficiency. I want to talk a little bit here about motor neurons, or sorry, motor units. Motor units, all the fibers controlled by a single motor neuron. The number of muscle fibers in a motor unit can vary greatly, and the fewer the number of fibers in a motor unit, the more precise the contraction. The muscle fibers in each motor unit intermingle with that of other motor units, and then the smooth but steady increase in muscular tension produced by the increasing number of active motor units is called recruitment. A variable number of motor units is always active, even when the entire muscle is not contracting, and this creates a resting tension called muscle tone. During a sustained contraction, motor units are activated on a rotating basis, and that's called asynchronous motor unit summation. This ensures that each motor unit has the opportunity to recover before it's stimulated again. Here you can just see a graphic of the characteristics of smooth cardiac and skeletal muscles.